Still
Okay.
recording.
All right, I'm sharing my screen. So these are the problems I wanted to discuss from this contest. So I'll do it in increasing order of difficulty. So first there's H, which, so the problem is, it's pretty simple. So you have to produce a longer howl than they give you, and there's certain rules that they say about what's allowed in a howl. And so there are two different like main solutions. One was to like construct, well, one was to think about the rules and construct like a howl of an arbitrary length, and then we can just output like one of one larger length than the input. And another solution, which is the one I did, was to see was to realize that the input is guaranteed to be a valid howl and follow these rules. And if I just need to make a longer one, I can look at the rules carefully and I can see that there's no rule preventing me from adding an O to the end. Like if I add an O to the end, it won't break any of the rules. So my solution was just to add the character O to the input and output that. So
Yeah, I
I don't
think
know.
that's really cute. Yeah.
And I think I saw that like solution slides from this contest, and I think they mentioned both of those things. I don't think there was like a third idea. Okay. I don't think there's anything else to discuss about H, but it's kind of funny. Next there's F. I'm skipping some problems like C, which I really didn't like because it was like the hardest part was to understand what it was saying. Okay, so for F, we have this is a bowling alley, and it has a certain length and a width. And our bowling ball starts here, and we can choose to launch it at a certain angle alpha. And it gives some formula for how it bounces off. And it says that the angle is like some function of alpha. So then it bounces there. So then here it would bounce off with angle f of alpha. It's like you apply to the function to whatever angle it comes in as, and then that's how you calculate the outgoing angle. And so the goal is we want it to hit the center at exactly the length from where it started. And we want it to bounce exactly k times first. And the constraints were pretty small, so about like 10 bounces, the width and height are pretty small. So, and the function of alpha is arctan of 2 tan. So there were two different solution ideas. One was to like look at this formula and try to solve it mathematically. Like you can realize that if you apply the function to it again, you kind of undo the tangent from the previous time. So like if we have, so we have arctan of 2 tan at first. Then we have arctan of 2 tangent of arctangent of 2 tangent. So you can see that the tangent and arctangent are inverses of each other, and then we end up getting 4 tangent here. So then similarly, it goes to like arctangent of a power of 2 times tangent. So I didn't solve this problem mathematically, but I believe you can use this idea to sort of calculate for a given angle, like how far it will be, and like whether the angle is too small or too big. So or maybe to and then maybe
I'll
to
talk
solve
about
for it
that.
directly.
I'll talk about that in my video. Yeah.
Okay.
I think it's really depending on the first instinct. I think for most of us, most of who write program, you look at it and you think by sections, you don't, and you see it's relatively straightforward to implement. So you don't really think, which is I think really perfectly.
So yeah, the way I implemented was binary search instead. So the idea is clearly if the angle is really small, then I'll have to bounce way too many times before getting to the center. And if the angle is too large, like if I go directly forward, then it doesn't bounce at all. So that's not a so it gives some intuition of like one angle's too small, one angle's too large, so something in between is just right. And actually, you can binary search it. I'm not sure if I think the fact that this is an increasing function in alpha proves that there's exactly one angle that is correct, and for less angles it will bounce more times, and for larger angles it won't bounce enough. So let's say we have a given angle that we want to check. So I think one interesting question is, what exactly do you check? Do you check, do you simulate it until it passes this line and then measure how many bounces and if it's to the left or right of the center? And I believe that approach is bad, because if like you test a bad angle, then the complexity will be number of bounces, which could be very large. But what I did instead of that was, in the simulation, instead of bouncing until it passes this line, I make it bounce k times and then hit the center, and then see if it was below or above this line. So then the complexity is k times number of iterations of the binary search, which is log of whatever precision I want. So it would be log of 1/epsilon. And so when binary searching over doubles, like if you're binary searching in an array, then it would terminate at some point when there's only one element left. But here you should terminate when further iterations would be unnecessary, because it's already within the precision that you need. Is this good enough? Any questions?
Yeah, I did the same way.
All right, and then next is J. Is there a way to... All right. So now we're on J. Oh no, there are faces in the way. There. So this problem was pretty straightforward in understanding what to do. So the problem is you have some books with different titles and different numbers of pages, and also there's events like a friend gives you another book with a number of pages at a certain time, and it says that you'll always read the alphabetically first book that you haven't read yet, and then it takes 1 minute per page, and then once you're done, then you look at what's the next alphabetically smallest book left, and then you continue. And the question is, what time do you finish reading this particular book, Jane Eyre? So the solution is essentially to just like directly simulate what it's saying. Like you want to sort of process queries of like, what's the smallest book? Like, what's the smallest available book at time t, and then sort of remove it from the list of available books. So these are like the questions you need to answer. and then you can just directly simulate the process of choosing a book. And then once the book is Jane Eyre, then you like output the time. And then, so yeah, it's pretty straightforward simulation like that. And the way to remove the smallest book is these are very similar to the operations that you do on a priority queue. Or you could just sort them. I guess you don't need a priority queue, but this is what I did. So essentially, I start with just the books that are in my pile. And then every iteration, I insert all of the books that are before the current time into the priority queue. And then I choose the alphabetically smallest one and then add its number of pages to the current time and just repeat like that until Jane Eyre comes up. And so actually, like, the other part of this problem that's hard is just reading the input, because you'll notice it's not entirely friendly because the titles are in quotes and separated by spaces. So that's actually an additional challenge to the problem where you have to parse the input correctly. And so, like, one way you can do this is to read the entire line and then find the two quotes and then take substrings for the title between the quotes, and then take the substrings that correspond to the numbers and then convert the numbers, or convert the string version of the number to int. And then so that's not that's a little bit more annoying to implement, but it turns out that in C++ there's a feature in reading input called delimiter. So normally when you say like get line, it will read all the characters up until the next new line character. So the way it does that is it reads everything up to a specified delimiter, which is by default the new line. But you can also specify it to be another character. So you could specify the delimiter to be a quote, and you'll read all the characters up till the next quote, or read a number until the next quote. So in that way, it's pretty friendly, and it can make the implementation a little cleaner. So that's good to know. Any questions about J?
Yeah, I just want to add that you can also use a set, which is a little bit overkill, but it's the same thing. You want to order those access, and because there's this event that new books are added, you cannot quite just use a vector and then sort, because then you need to insert, and that becomes too expensive. So you basically need to dynamically insert things and then finding the smallest at the particular time. So that's where priority queue and set provide.
Yeah. So priority queue, it does, like, the operations a priority queue does is a subset of what a set does. Priority queue might be preferred because it can, like,
it should be slightly more efficient.
Yeah, slightly more efficient. And also, I think, so a priority queue by default allows duplicates while a set doesn't. You would need to say need to say multi-set if there were duplicates. In this problem, there shouldn't be any duplicates, but
yeah, and in Java you use tree set, and the functionality that set provide but priority queue doesn't provide is to find an element in it, sort of do binary search in it. So that priority queue does not provide. Priority queue only give you the top or the top element.
Yeah, so it's definitely good to know about those data structures that are already implemented in the standard library. All right, so I'll move on to E. So this problem says we have a tree and we want to visit the nodes in some order. And then for each node, we will count how many of its neighbors were visited before it and how many of its neighbors were visited after it. Then we'll consider all of the all of the differences between those two numbers, and we want to minimize the number of distinct values. So I'll give an example. Like, let's say I visit 0, 1, 2. So like this is the order we visit them in. So now node 0, it has 2 that are visited after and 0 that are visited before. So we add 2 minus 0 to the set. So we have 2. For 3, we have an absolute difference of 1. For 2, we have 0 and 1 that are before and 4 that is after. So that's also a difference of 1, so which is already in our set. 4 is a difference of 1, 1 is a difference of 1. So there's 2 unique values here. So the answer, in if this was the correct ordering, then the answer would be 2. There's 2 distinct values. And we want to minimize the number of distinct values. So one observation is is also just in the title. Like we want things to be pretty balanced.
Sorry, right? So in the example, I think the leaf are also unbalanced, right? So the leaf are, so it should the correct answer be what was the order that's outputted? Is this the number, the order they're outputted?
The output is the ordering that minimizes.
Right. No. I mean, in your example, the picture you just saw. So the number is the number that they are outputted, or there's some other outputting order.
The number I write is like the index of the visit. So like 0 means it's the 0th one that I visit.
Okay.
1 is the first one I visit.
So you said 0 and 2 are unbalanced. That was or. You said answer is the two, they're 2 unbalanced. Is that 0 and 2?
We're not minimizing the number of nodes that are unbalanced. We're like measuring a value for each node, which is the difference of, like it says in the statement, AI is the number of neighbors that were visited before I, and BI is the number that were visited after. And we consider the set of numbers of AI minus BI.
Oh.
I think
my understanding is slightly different. I think my understanding is minimizing the number of unbalanced nodes. So for every unbalanced node, then you will get one complaint letter. So we want to minimize the total number of complaints.
I think I had that interpretation during the contest, and I think they're actually, like the solution you would think of is actually correct for both.
Yeah, so I don't know exactly which one you intended, but whatever.
I think if you read it carefully, it's like for every number, the 2 numbers differ.
But what does that mean?
It doesn't say a condition like for every time that they're different. It doesn't say that. It says like for every number they differ by, there will be a complaint. So it's like.
All right. Okay. But yeah, I see. So yeah. I guess it is possible to come up with a solution for the second interpretation that will be wrong. So, but I guess most naturally when you try to do it, you will make the balance the difference either 0 or 1. So then in which case it's actually also correct for this interpretation.
Yeah. So the observation is you can make everything 0 or 1 by sort of like you do a depth first search on the tree. So we can kind of say, so for the root, if it has an even number of adjacents, we want to make half of them like after it and half of them before. And then we get a difference of 0. Or if something has an odd number of neighbors, then we can try to force it to be like, it doesn't really matter if it's like floor of n/2 and ceiling. Doesn't matter like which one is which, but we just like make the absolute difference 1. So if you can make them all 0 or 1, then it's a solution. And we know we can't improve it because the parity of the degree of a node fixes whether it can be a 0 or 1. Like we can't, like if we have the solution with all 0s and 1s, then we can't make it all 0s because an odd degree will always be odd and an even degree node will always be even. So if we just try to make everything 0s and 1s, it will work. So the way we do this is, like say we start at the root. we split up its children into like before and after. So then we'll solve for half of them. Then we'll visit this node. Then we'll solve for the other children. And there's one catch, which is when we DFS and we solve for a child, we have to keep in mind what the parent's value is, like whether it's greater or smaller. So you have to mind like edge cases like that, and whether the parent is smaller or greater, and then that'll inform like whether you split this n over 2 plus 1 or minus 1. So you have to be careful with like off by 1 errors there. But yeah, that's essentially the solution.
Yeah, I just want to add, so I think computer science students are familiar with pre-order and post-order traversal. So you pre-order your output yourself first and then visit your children. Post-order, you output your children first. And now this is like a mid-order traversal. So you output roughly half of your children and then output you, and then you output the other half.
Mm-hmm. Yeah, so there's like in order, which is like that, but only on binary trees.
Yes. So it's a general case of in order.
Yeah. So that's the solution for E. Next is G, which is also a tree problem. So in this problem, we have a tree, and like each node has a what do they call it? The GDP of each city. So each city in a tree has a GDP and it has a population. And so the goal is to take a connected set of nodes that include the root, and then consider the GDP per capita. So that would be sum of the GDPs divided by the sum of the populations. And we want to maximize this. So so to me, this problem seemed very like unapproachable. Like this average is sort of unfriendly. Like you can't do something greedy, like start with just the root, and then as long as some child will improve the GDP per capita, add it. So a greedy approach won't work because you're because sort of properties of fractions don't let you do things like this. Like there's no inequality like this, I believe. So it doesn't, so it's kind of unfriendly to greedy approaches, and DP approaches also don't seem to work out. Like if we found the maximum GDP of each subtree, and then try to combine them in some way, it doesn't seem to work out because it's hard to recover what the overall GDP per capita would be given like separate GDPs. And so the solution is, it reminds me of I think a CP2 homework problem from the fall. I forget what it was. But essentially, like if we had some average like this, we think if we can binary search it. So like, let's say we want to know if it's possible to achieve a GDP per capita greater than some value A. Then we can rewrite this as sum of C greater than or equal to A times sum of K, or sum of C minus A sum of K greater than or equal to 0. And actually the sum kind of combines. So like you can say sum for each node U, C of U minus A K of U is greater than or equal to 0. And sort of this sum is in a much more friendly form, where the C and K aren't like separate objects anymore. Like now each node has a singular value, C minus AK. And so the question now is, can we select some nodes containing the root where the sum of these values is non-negative? And then the binary search works out because if it's possible to achieve a GDP per capita greater than or equal to A, then we know that the answer is greater than or equal to A. But if it's not, then we know the answer is less than or equal to A, and we can binary search that. So now we have to solve this problem where each node has one value. Let me just call it like AI. And we want to know if we can make a connected set where the sum is greater than or equal to 0. And now a greedy approach actually does work, where or I guess it's DP, where for each subtree you check if you can contain the root to make a greater than or equal to 0 value. If you can, there's no harm in adding that to the root. But if you can't make a greater than or equal to 0 sum, then there's no reason to add it to the root. It will only like make the sum smaller. So in that way, you can like you want to find, so like you say dp of u is the maximum like sum of values in the subtree of u that contains u. And the way you compute it is by computing it for all the children and then only adding the dp values of the children that are greater than or equal to 0. So at the very end, you just check if dp of the root is greater than or equal to 0 or not. Are there any questions?
Yeah, I just want to add, at least for the, unless you have very difficult optimization problem, basically if DP doesn't work and greedy doesn't work, it's got to be bisection, binary search.
Mm-hmm.
So, and this this average sort of average by itself, combining them have the difficult property doesn't combine well. But once you fix a particular target, then these things become much nicer. Yeah,
Mm-hmm.
and the tree property is a kind of you either include this whatever the final subtree that you select will be the whole tree with some subtrees completely removed. So
Mm-hmm.
I guess yeah, that's sort of what give rise to the DP interpretation.
I think if you see like this kind of problem for the first time, it can be a little hard to come up with because like sort of you start with saying like let's just say if we want to check if it's greater than or equal to A, it's like where did this A value come from? Like it doesn't like if you don't see where it leads, it's hard to think of it if you haven't seen similar problems, I guess. But yeah, I think but that's why like generally you tend to think of greedy or DP approaches on this kind of problem to start with. But when they kind of lose hope, you have to go in a different direction. Okay, next is problem I, ice cream. So in this problem, it tells us that there's an ice cream maker where there's like this graph where there's a chocolate node, a vanilla node that can produce chocolate and vanilla. And there's some pipes between different junctions. And then there's a mixer labeled F. So each pipe has a certain capacity or like a weight. And that means how much ice cream can pass through the pipe in either direction. And the problem is we want to produce ice cream that's equal parts chocolate and vanilla. It needs to be produced in the mixer. And we want to know how much of the ice cream we can make, like per second or per unit of time. So like the capacity says like we can pass W units of ice cream through a pipe in a second, and we want to know the rate that we can produce ice cream. So if you know about max flow, it's very obvious that this is a flow problem because it's stated like exactly in terms of the way flow is usually described. Like you have things passing through pipes, they have capacity. We want to like send the maximum amount through the structure. And but it's not easy enough to just say it's flow. So typically in a flow problem, you have a single source and you have a single sink. And you want to know how much you can send from the source to the sink. So in this problem, you might think there's two sources, so we can just like create one source that leads to both of them. So the problem here is that in the problem, we specifically want to make equal parts chocolate and vanilla. So like if we just made this graph and asked the maximum amount of ice cream we can make, it wouldn't ensure that condition is met at all. So we have to think about what we can do instead. And again, it's actually binary search. So what we have to do is like we can't make these. So what I said before, like we would make these infinite capacities, but then it might not be balanced. What we can do is make them the same capacity X. And we want to check if we can make at least X amount of each part per second. So the way we do that is make these capacities the same as X, compute the max flow, and then check if the flow is 2X. So if the flow is not 2X, that means we cannot make X or more ice cream per second of each part. But if the flow is 2X, then that means we can make at least that much. So the solution is like to binary search on X and compute the max flow. But there's a huge trap. There's a huge trap, which is, I'll give an example of where it came up. And I think almost everyone who got a wrong answer, like that wasn't from like implementation bug, was probably from this, which is, consider this case. Suppose each of these have capacity 1. Then actually the solution is to send 1/2 of a chocolate through here, 1/2 of a vanilla through here, and then 1 of each through here. So actually the correct X to assign for this case is 1/2. And then the final answer you output is like the total amount of ice cream, which is the sum of these. And the sum is 1. So like even though the answer is an integer, these values won't be integers. And that's the tricky case you have to think about, or you might not, or you won't solve it. But then when you see this, it's not obvious actually that these will be half of an integer. It turns out to be true that if these are if you test any half integer, it will be correct. I actually tried to prove it, and it's kind of non-trivial, but I can prove that like these have to be half an integer. But you can also guess because the output specifically says a single integer. So you know that 2 times that value is an integer because the output says so. But I think it's kind of interesting to think about why the answer will be an integer always.
So you said the trap is essentially like a precision problem.
The trap is that in max flow problems, you typically think everything's in integers and it will just work out.
Right.
But here we actually need to think about like real numbers. Now you can avoid like having floating points in your code by just multiplying everything by 2. So like instead of 1/2 in that case, you just double all the weights and then try integers for this number.
So basically, the MacFlow algorithm deal with integer or at least discrete capacities.
Yeah. So maximum flow is stated in terms of real numbers, but it has integer solutions if the capacities are all integers.
So what the MacFlow algorithm do you typically implement? Which one do you use for this problem?
For this problem, the constraints were pretty small, so I just used Ford-Fulkerson. So there are faster flow algorithms for special cases. In this case, so the complexity of Ford-Fulkerson is its number of edges times the flow. So a number of edges is 1,000. And the maximum flow is like for each outgoing edge times the capacity. And the capacity is, oh, the capacities are kind of large.
But yeah, but the complexity is only in the worst case, right? So when you actually run, well, it's unless they're specifically set up for the test case are carefully selected, you won't reach that worst case, right?
It's pretty hard to make an example where
it reaches
where it actually achieves this worst case.
Yeah.
So maybe it's not really guaranteed that Ford-Fulkerson is fast enough. In any case, there's there's Edmonds Carp, which should run in E squared V. So that's like 200 million in 5 seconds. That should pass. And also, it's like it won't generally reach that.
Yeah, binary search. You need. Well, I guess if you do a search for integer, but if you search for integer, there, I guess like 10 step or something. I don't know.
Yeah. But it's generally hard to make like worst case flow.
Yeah. Do you use the code book or do you actually just type it from memory?
I just typed it from memory. I didn't use the code book.
Yeah, I guess I had 1 hour left. Was wondering whether I should consult the code book, but actually I haven't. I didn't really thought about it enough to to realize these other things related to these problems.
Yeah, like the fractional thing.
Yeah. Okay.
So yeah, I think that's. I mean, maybe I could discuss the proof, but.
I don't think that's
not really.
Yeah. So Kyle, do you have questions?
No, I think you covered a lot of things that are very helpful though.
Okay, cool. I'm going to stop recording.